So now we can finally calculate the standard uncertainties in the slope and y-intercept. But first we need to calculate what is sy squared. So from the previous slide, sy is equal to the square root of the sum of di squared divide, I'm going to put that on the inside of the parentheses, by n minus 2. So that would just be 4. So if I rewrite this with our numbers, that would be 0.076923. And remember that this is not then squared again, because this was that sum of di squared. So don't get confused and re-square this. I made that same mistake, so learn from my mistakes. N minus 1. So sy is equal to 0.19611. Now let's figure out our uncertainty for the slope. So um squared. So that's um squared. If I wanted to just figure out what is just the uncertainty, I would then square root it on both sides to get rid of that squared. So I'm just going to save a little bit of time and just solve for the squared, square rooted version. So that's going to be 0.076923. Now we're going to square it because that's equal to sy. Oh, sorry, we solved for sy. Times n, which was 4, and divide that by d, which was 52. Now let's do ub. So I would just square root that to get rid of the square on both sides. And if I recall the sum of x squared, that was 62 divided by d, which was 52. So my uncertainty of my slope is and my uncertainty of my y-intercept is. So now let's write this with everything included. So here's our slope and our y-intercept. Let's include the uncertainties. So our slope's going to be plus or minus 0.05439. So if I was to use the rule of significant figures, I would say this is going to match up with here, 0.6. I'm going to round up and then keep that as 0.05. Now let's do the same with the slope. And according to the rule of significant figures, I would just take the first non-zero digit in the uncertainty, match it up with the same decimal place or digit in the answer, and rewrite it. So 1.3, I won't be rounding, plus or minus 0.2. And you could also write the equation out like that too. So y equals mx plus b, but you can also use these values in there. I think so. So that would be y equals, so m 0.62 plus 5x plus 1.3 plus or minus 0.2. So you could write it either way. So this is how the book did it. They kind of like, I broke it down and did little part, like by little part, but this is kind of how they summarized everything in the book. And this is just matching up the numbers that we just calculated. So we did the math here. And we matched our digits up. So you can also include the insignificant digit if you just do a subscript on it. So we got the right answer in the end. Okay. So to express uncertainties as confidence interval, multiply the standard deviations by the student's t-value for n minus 2 degrees of freedom. So if our n was 4, our degrees of freedom is 2. So we would have to multiply that by our t-test. So this would be our overall uncertainty for everything for the confidence level. So there is a function for least squared method in Excel. So that was everything on how to do it by hand. But if you type in the linist function in Excel, it will do it for you. And I'll be honest, let Excel do this for you. Like, I have to teach you how to do it without Excel, but if there's an easier method, just use the easier method. So you would highlight, let me get my yellow number. You would highlight the column and rows that you wanted to do least squares with. Then in a box far away, you would type in LIN or equal sign LINEST, open parentheses. Then you would do the y's, comma, known s, comma, true, true. So you would essentially use this equation. So linus, so they do B2, comma, B5. That's going to be your y values. So that's what they did here. Your known y values was B2 to B5. Then they did A2 to A5, which was your known x values, comma, true, comma, true. And then for PC, you do Control Shift Enter. Max, you press Command Return, and essentially it gives you this. It gives you everything we just spent 20 minutes doing in a fraction of a second. So please practice using Excel to make your life easier. Okay, now you know what R squared is. You've used R squared so much before now, but do you know what R squared means? So we all know that the closer R squared is to 1, the more linear it is. So it's a conservative measure of closeness of fit is the square of the correlation coefficient. So essentially, however close your line of best fit is to a true line is going to be what R squared represents. So the goodness of fit is judged by the number of nines. And R squared of 0.999 represents a better fit than 0.99. And then an R squared of 1 represents a direct correlation between the two variables. So this is often considered overfitting of the data. So you're really never going to get data that has an R squared of 1, but we will say having an R squared closer to 1 is better. So this is how you can calculate what R squared is using the data we had already used. So we already know the sums here, but that's essentially what Excel would spit out at you, but this is how Excel calculated it.